logo. So remember how a while ago I won that little competition thing for having the shortest number of instructions for that assignment? Guess what? I beat the TA. Well, as a reward, I got a book for that the professor had sent me. So now it's just arrived and I'm going to go and get it. Oh yeah, and for the specifics of how I actually won that little competition thing, there's like a link up here. You can see it, there's a whole video on it. Oh, actually, speaking of that coding assignment, the assignment that I had right after that was actually to build a CPU in Logisim. And I was going to make a video about it earlier, but the homework was still ongoing earlier, so I didn't want to make a video of the homework. So now that the class is finished, I can show you that CPU. Also, multivariable calculus just started today. Well, it technically didn't start today because the professor just talked about logistics and there wasn't any actual calculus involved. But it started today. And I think it's going to be fun. So, we'll see. Almost there. And we are here. So, the mailbox is just over there, and I don't want to have to go into the parking deck because that's a lot of works, and I'm technically not supposed to park here, but I'm gonna park here. Okay, so I'm guessing the heavy one is the book, but there's also a mystery package. Oh, and look, my car didn't get towed. Okay, so I have a hunch what this mystery package might be. Because a while ago, I got a free Google Nest from having a YouTube Premium subscription. So I am guessing that's what it is. We'll find out later. Also, I haven't had breakfast yet. Maybe I should have bubble tea. Yes, I'm gonna have bubble tea. Also, the bubble tea place has great waffle fries, so I am going to get that as well. I now have bubble tea and food. And it's always a pain to try to get out of this bubble tea place because it's a one-way parking lot thing with a very narrow back alley that I have to take in order to get out. So yeah. Okay, I made it. Alright, now time to test out my theory. First I gotta get some lights in here. They're just gonna be cut. There we go. Yeah, this mess was still here. This table was clean for a total of 2 days, and now it's like this again. And I was correct. Cool. And the book I got is a coding handbook, which could be very useful. Okay, I'm gonna eat my food. Where's my food? Oh, here it is. Okay, so I recently got a whole bunch of electronics components, so I decided to make a little cool something here. Don't mind the wiring, I know I have messy wiring, I'll fix it later. So basically this is an AC voltage detector. This little loop of wire here kind of acts as an antenna, and it's kind of fed into a kind of a cascade of 3 transistors. So each of those amplify the tiny signal that this thing gets by about 200 times. So in the end, we have around an 8 million time current amplification that is enough to pass enough current through to drive this LED and this piezo right here. So to test it, I'm going to turn on this soldering iron. So now there's AC voltage coming through this. And if I hold the tip of this near the thing, it should light up or make a noise. There we go. Don't know if you can hear the noise, but it's definitely lighting up. Pretty cool. But yeah, anyways, I said I was gonna show you that whole CPU thing, so let's go do that. This week's homework is designing a CPU. So let's get started. So essentially, this is what I'm trying to make. Now, I've seen this diagram so many times during lecture and in the textbook, it is pretty much burned into my brain right now. But basically, this is pretty much what a CPU does. Well, what it should look like. Well, they don't actually look like that, but like, let's start with the register file. So we have already built a register file for recitation. This is a 16-bit register, so there are 16 D flip-flops, and they basically store whatever values you put into them, and they will output that value, and that will be later taken and read by some other parts of the CPU. A register as a module has a clock, a write enable, and a reset. I am going to black box it and basically abstract it into a component that I can copy and paste, so I don't have to do this whole thing for every register I do. Now this is one register, so to make a register file of, how many bits does the register file have? So the particular CPU that I am making has 8 registers in the register file. So here are the 8 registers, all nicely wired up, or not very nicely wired, but decently enough wired up. Now let's start working on the ALU. Alright, so the first step of making an ALU is making an adder, and this is the logical circuit for an adder. For a 16-bit add, we just have to chain 16 of them together and wire them nicely, hopefully. So here's a 16-bit adder. Now we can use this thing as its own module and just stick it into the ALU. Actually, before I do that, just to make sure that this works, I'm going to test this. So I'm going to say, what is 1 plus 1? And the answer is indeed 2. So this works. Now, knowing that this works, time to back up to GitHub. It's safe to Git. Okay, let's keep working. So for the purpose of this CPU, we have 16 instructions in the instruction set, which means that the opcodes are 4 bits. For the add, we can just take that adder that we just made and set the subtraction bit to 0 and feed it into the multiplexer. Okay, now this ALU can do addition, subtraction, XOR, NOT, and OR. And I have also added an extra output that turns on if the result of a subtraction is 0. So now connecting my register file to my ALU, and we have what is beginning to look like a CPU. Now we just need to add in more wires for all of the other instructions that this CPU will be able to accommodate, which I have started to list over here. I spent the most of past 40 minutes trying to implement the shifter, the bit shifter, which isn't hard, but is just very annoying because for a 16-bit shifter that can shift by a maximum of 7 bits, we have to pretty much do 3 times 16 multiplexers. Yeah, it was annoying, but it's done now. Alright, so I've been continuing to implement the rest of the CPU. I got up to store word, and I haven't gotten to any branching instructions yet, so this program counter and the instruction memory is still kind of here floating around, but I will connect those soon. I've also filled out more of this table. Alright, day 2. Now I have implemented the shifter and connected it to some muxes. All of these multiplexers are for jump and branch commands. And then this here checks the sign bit if it's a 1 or a 0, and that determines whether a number is less than another number. So now all that's left to do is jump and link, input and output. We're almost done. Now I have finished filling out this truth table correctly, I hope. So let's start implementing the control unit. So this control unit has as many outputs as there are columns on the table. And additionally, it has these outputs that corresponds to different fields in the instruction. So now is basically just seeing which ones on the table are 1 and using logic gates to turn these bits on and off. Okay, so now as you can see, I have the control, which is this big L-shaped thing over here, and I have gone ahead and connected all the outputs to the corresponding inputs in the rest of the CPU. So I am going to run this through the autograder and see if this thing actually works. Okay, so I just ran the auto tester, and I see that it failed the what is this? The bit shifting test, control flow test, and the recursive test. So let's go and see what's wrong here. Okay, I found one mistake in my control, and now I fixed it, and the shift is now correct. Now let's look at the control flow one and the recursive one. Okay, I found the issue. So over here in this little place, I had a NOT gate, because I thought, when you subtract one thing from the other, if the sign bit is 1, that means the other thing is greater than the thing. But then I was like, wait, sign bit is 1 means negative. If one thing subtracted by another thing is negative, then that means it's less than. So there shouldn't be a NOT gate here. So I removed the NOT gate, and now both of the other things work. So I think I am done with this CPU. Well, that was really fun. Now it's time to go eat food.